Today, I wanted to talk about a concept that I personally find really interesting: quantum tunneling. So what exactly is quantum tunneling? Well, first imagine that you had a ball and some kind of barrier, say a hill. According to classical mechanics, unless you give the ball enough kinetic energy to overcome the potential energy of the hill, it will never end up on the other side. Conservation of energy, pretty straightforward. Now let's say the ball is a subatomic particle and the hill is a potential barrier. In this new setup, things can get a bit weird. You see, occasionally an electron fired at the barrier will be found on the other side, even if it didn't have enough kinetic energy to overcome the barrier. This is called quantum tunneling. So why does this happen? Our world is governed by classical mechanics and is thus deterministic. Even the results of seemingly random events, such as dice rolls or coin flips, could theoretically be predicted with 100% accuracy if we had enough information like how exactly they were thrown. In contrast, the quantum world is largely probabilistic. As the Heisenberg uncertainty principle says, it's impossible to simultaneously know the exact position and exact momentum of any particle at any time. And this uncertainty can't be eliminated by designing better measurement tools. It's simply a fundamental property of quantum mechanics. So, we often represent a particle's position with a wave function which tells us the probability of finding the particle at different positions. Now, treating the electron as a wave, what would happen if it were to approach a potential barrier? Since it doesn't have enough energy to overcome the barrier, it would simply be reflected. So, how does quantum tunneling fit into this scenario? Well, quantum tunneling happens because something really cool happens when a wave, such as light, travels through two mediums. I'm sure we all know that at the boundary between two mediums, light can bend or refract, but it can also be reflected, and the amount of light reflected depends on the angle it hits the boundary. Now, there is a certain angle known as the critical angle where the light is completely reflected in a phenomenon known as total internal reflection. So is 100% of the incoming light reflected? Well, yes, but actually no. See, there's a set of equations known as Maxwell's equations, which pretty much summarize the fundamentals of electricity and magnetism. And when these equations are applied to light in this case, you actually get a small wave that dies off exponentially. This is what's known as an evanescent wave. This concept can be applied to the electron's wave function. When it hits the potential barrier, an evanescent wave forms. This wave dies off exponentially, but never quite reaches zero. So as long as the barrier isn't infinitely thick, some of the wave can make it through the barrier. And since this wave function represents the probability of finding a particle at a certain location, there is a very small and unlikely, but non-zero, chance of finding the particle on the other side of the barrier. And if that isn't surprising enough, it's also possible to find the particle inside of the barrier itself. Okay, so quantum particles can travel through barriers, but why don't we see this kind of behavior in our everyday lives then? Well, simply put, there are too many quantum particles in everyday objects. The probability of a single particle tunneling is already very low in of itself, and so the probability of all the particles in an object simultaneously traveling through a wall? Practically impossible. But that doesn't mean quantum tunneling doesn't have its uses. For one thing, nuclear fusion at the core of stars wouldn't be happening if it weren't for quantum tunneling. Take the sun, for example. It releases energy by fusing hydrogen atoms. Hydrogen atoms carry a single proton, which makes them repel each other with a force called Coulomb repulsion force. Even the immense heat and pressure at the core of the sun isn't enough to overcome this barrier, but quantum tunneling is what allows them to fuse. And although the chances of any individual atom tunneling into another atom is very low, there are enough atoms in the sun that these rare events happen all the time. Other than that, quantum tunneling is also used in transistors, plays a key role in DNA mutation, and is even used in some microscopes. So in the end, quantum tunneling is really just another cool result of wave-particle duality that shows how counterintuitive quantum mechanics can be. But for an event so unlikely, it seems to have numerous applications in every aspect of our universe. I hope you enjoyed this video, and thanks for watching.